And next I'm going to discuss commutator algebra. So the commutator of two operators A and B denoted by AB. So then I can define the commutator like this. So sorry. The commutator of two operators A and B denoted by A and B is defined by like this. A commits with B equal to AB minus BA. So for example, in case anti-commutator of A and B, I can write like this. Anti-commutator of A and B. A comma B square brackets. Here I'm using plus. This means anti-commutator equal to AB plus B to A. These are very useful notations in quantum mechanics, especially in case if you are going to derive Pauli's exclusive. So Pauli's spin matrix properties, these are very much helpful, these two notations. The Dirac's 4x4 spin matrix or Pauli's 2x2 matrix. These are very useful. Two operators are said to be commit if their commutator is equal to 0, and hence we can write A equal to B. I mean AB equal to BA. It's better to write here. Just wait. Two operators said to commit if their commutator is equal to 0. Then we can write this A B, this one A B minus BA equal to 0, right? A B A B minus B A equal to 0, which means commit right A B equal to B A. Any operator commits with itself, then it goes to the 0. For example, same operators are there, A and A operator, then it gives you the 0. Any operator commits with itself, that means if A is one operator, A is another operator, same operator, is equal to 0. So here I am going to give one note here, important one. If two operators are Hermitian and their product is also Hermitian, if two operators are Hermitian and their product is also Hermitian, these operators are commit. So for example, here I'm taking A and B. These two are the product of two Hermitian operator. Then it gives the we know B dagger, A dagger, which means B and A, right? Since AB dagger equal to क्या इससे that is equal to A into B. So we have already, if they are commit, we can write like this, right? Okay. So examples of these commutator things, commutator of position operator, X of their momentum operator. For example, here I'm taking the position operator X. I'm going to write this momentum along the X component. So apply these commutation rules. X px minus pxx, that equal to, so in place of x operator in quantum mechanics x, so momentum operator we know IH cross d by dx minus IH cross d by dx into x, d by dx of 1, this term is 0, minus into minus plus, d by dx of x is 1, remaining thing is h cross. So the value of position and momentum equal to IH cross. Similarly, you can try different type of components. If you take y component along y component of momentum equal to IH cross, and z component along z component of momentum can get IH cross. The reverse of these components, if you take px comma x commutation algebra, you can get minus IH cross py into y, in case if you get minus h cross pz z component, you get minus h cross. You may check these things for practice. X component, py component, and y component, pz component, z component, px component. You get answer is equal to 0. Then you may check these things. And some properties are there here. Properties of commutator, very important, these things. Properties of commutators. Number 1, anti-symmetric. A operator B minus B comma A. Second one is the linearity. A comma B plus C plus D plus and so on. You may get A B plus A C plus and so on. Next, third property is Hermitian conjugate of commutator. A B, if you apply the Hermitian conjugate, you get B and A diagonal. This is Hermitian conjugate of it. Next, fourth property is distributivity. So in case A, B and C is there, then you can apply like this: A, B, C, and B, A C. This property is very important whenever you calculate the angular momentum operators Lx, Ly, Lz, or you can get some commutation relations. So these are very useful in distributive law especially. Next, fifth one is Jacobi identity. Even in our classical mechanics also there. Proof of this Jacobi identity in bracket notations is very important. A B comma C plus B C comma A plus C A comma B. This is Jacob identity. So A B C is there. So if you fix A, you can get bracket BC. If you fix B, you can get bracket CA. Okay. If you fix C, you can get bracket AB. This is the sequence. Don't miss this sequence. Then only we can call this one Jacobi identity. Next, sixth, operator commit with scalar. So one operator is there, B is a scalar, then it gives the 0. So seventh, here I'm going to use mathematical differential equation. D by dx is there, and here x is there. So what is this answer? 1, right? So apply d by dx is x minus x d by dx, that is equal to, this one is 0, this one is 1. 1 minus 0, that is equal to 1. Next, in case x d by dx is it, so x d by dx minus x d by dx, you get here minus 1. Next, final one, this one, eighth property, A operator is an inverse operator, is it? Inverse operator. Okay, so A inverse minus A inverse A, that is equal to 0, because A inverse equal to A inverse A is equal to I.